Hello, welcome back to Organic Chemistry. In this video, we're going to learn about synthesis and retrosynthesis. Now, this is a very important topic, and it's something that you're going to do throughout the entire year. So, synthesis is the foundation of organic chemistry. Everything that we learn is about somehow related to the idea of synthesis, okay? So, we're going to learn all about it today, and basically what we're going to do is we're going to start with these topics here. Now, this video series is going to be a little bit different than the other ones, where I'm not going to have a video for each section because it really isn't that much time per section until we get to the end, okay? So what we're going to do is we're going to build a story together. We're going to start with the foundation. We're going to understand the basics of what a reaction is, and we're going to bring our way up to the point where we can do retrosynthesis. So synthesis and retrosynthesis. Okay? So let's get started, and you'll see the path that we're taking is actually a very intuitive path. It's going to help you to learn this really well. All right, so the first thing we're doing here is we're talking about what a reaction is, right? So let's start there. A reaction is a combination of bond breaking and bond making that occurs in order to make a new product or a new molecule. Okay, that's all we're doing. It's a chemical change in a structure or in a system by breaking and forming bonds. That's it. That's a reaction. Now, reactions can be classified into different types. Now, this is really useful because you see over here, these reactions right here, A, B, C, and D, this covers almost all of organic chemistry. So after I describe what these are right here, you could turn to any page in your textbook and it's going to be one of these 5 reactions. That's it, 4 reactions. It'll be one of these 4 reactions here. Okay, so let's take a look at the first one. The first one is known as an addition. And what an addition means is that you're taking 2 molecules that are independent of each other and you're making them into one. Okay, that's known as an addition reaction. I'm going to give you an example of that. Let's say I have a carbonyl group, and you, by the way, you don't have to know these examples. You just have to get the idea of what's happening. So if I have a carbonyl and I add water into this environment, then it turns out that what you wind up getting is this structure here. So what actually happens here is these 2 pieces, A and B, are coming together to make C. So that's the process that's taking place here, okay? And so notice how all we did is add 2 things together. That's known as an addition reaction. And again, there are many addition reactions, and we're going to learn a lot throughout the whole year, but this is the general template. Now, an elimination would be the opposite of addition. So I'm not going to use this example, but if I have, let's say, let's do a Br right here, alkyl bromide, and I add a base, let's say CH3O-, and they react together. So what we actually do here is we're going to take this right here known as C, and the CH3O- is actually not, it's the solution, right? Because this is methanol in methoxide is what we say. Now, these right here are going to work on this molecule C to make something new. We're going to eliminate things from C. So watch. If I was to take the H from this right here, this neighbor H, and pull it off by using a base, this is an acid-base reaction, which is the carbon is protonating this CH3O-. Well, then this can go here and make a double bond and the Br can leave. So we've just eliminated from this molecule C an H and a Br. So we have that plus CH3OH plus Br-. So this is known as an elimination. From the point of view of C, from this right here, C, we've made 2 different things, actually 3. We've made this piece here by eliminating from that starting material a Br and an H. And that's it. So that's an example of an elimination. All right, the next one is known as a substitution. And this is where we're swapping pieces. So, for example, if we have, let's say, a structure that has, let's say, a Br right there, okay? And then I have, let's say, I'll put let me think, what do I want to put here? I guess I'll put H2O. Okay. Now, actually, I'm going to show the H2O out so you could see this clearly. So let's say it looks like this, okay? Now, if, let's say, this oxygen goes into the carbon with Br, and the Br leaves and takes the H from that oxygen, okay? So notice how it's not just leaving, but we're taking the H off of water. Then we make this right here, HBr, and we make water attach, or the OH from water attaching onto the carbon. Now again, don't worry about the mechanism. I just want to introduce you to the types of reactions that exist in the categories. Now this is known as a substitution because what we did is we swapped out pieces. So for example, if let's say this is A and this is B for the first molecule, and let's say this is C, oxygen, and this is D, then now we have a connection between A and C, and we have a connection between D and B. See how we swap pieces? That's what it's meant to be, a substitution. You're substituting pieces of each molecule with each other. That's it. Okay, the final type is known as rearrangement. Now, a rearrangement is also known, it's constitutional isomer. All we're going to do is change something within the molecule, but it's the same molecule. So A just becomes B, meaning we're not working on it with anybody else. We're just going to modify A and make it into something different, B. But it's the same number of atoms, the same formula. That's a constitutional isomer. So I'll give you an example. Let's say we have a system like this where there's a double bond on the end. And somehow at the end we make a system where the double bond's in the middle somewhere. Well, this is a rearrangement. We rearranged the double bond's location within the system, and that's known as a rearrangement. Okay, so rearrangements is the last category. So as I mentioned before, these, you just want to get a general idea of the type of reactions that exist, and these are them. There's only 4. Your entire textbook is made up of these 4. That's it. So if you turn to any page, you will see one of these 4 over and over again. Now, it might be harder to identify over others, but this is it. Okay, so it makes organic a lot easier to organize when you think about it from this broad point of view, that there's only really 4 things that are happening, 4 reactions, classifications. Okay, now let's continue. Now, the next thing I want to talk about is what's known as a reaction mechanism. What is a reaction mechanism? Now, a reaction, we already know, is breaking and forming of bonds. But if I want to describe the process that's happening, the actual events that are taking place, that's called a reaction mechanism. So a reaction mechanism is a detailed description of what happens to that molecule when it goes from the beginning to its very final endpoint. Okay? Now here's an example of that. Right now, if I have an alkene and somehow it gets a Cl added to it, and also, by the way, an H, which we don't really see, but I'll put it right there. Well, this would be what happened, right? That would say that this reactant, right, here's a reactant, and it becomes this product, right? But the stuff in between is describing what's happening. So in order for this alkene to become an alkyl chloride at the end, this is what's taking place in between. And so we have what we call in the middle intermediates. So this is an intermediate. It's something that's going to take place during its path or through its path to product. So you might have 1 intermediate, you could have 5 intermediates. So all the things that happen between reactant and product is called intermediate. And now in this case, all we're doing is we're breaking this double bond, we're making a carbocation. This is called a carbocation because the carbon is positive. We'll learn more about that after this exam. So we have a carbocation here, and then Cl is coming into it. Now, there are certain things that we could do to describe this reaction, and that's what these tools are below. The first thing is we could show electron flow, right? And we already know that this is telling us where electrons are going, not where the nucleus is or the atom, the symbol. It's where the electrons go. So I could say that this double bond is going after H. It's an acid-base reaction. This is a base. Remember, alkenes are common bases for Lewis acid-base chemistry, and this is the acid, HCl. So we're going to pull in the H. Cl is going to take the electrons away from H. Notice how we're describing where the electrons are going. And then after that first process, all of a sudden, Cl has electrons. It's going to give it to that carbon that's positive. So look what happened. Now carbon is accepting electrons. Remember, acids are positive or partial positive. And so now who's positive? Carbon. So this is now the acid. And since Cl has electrons, it is acting as a base. It's giving electrons to that acid. So that's all that's happening. This is two acid-base reactions back to get to that product. Now, you don't have to memorize this reaction because you're going to learn about it during your next exam. But you just want to have a general idea of what a reaction mechanism is. It describes the process of what's happening. All right, now we could talk about the energetics of a reaction, and that's just using an energy diagram. So we might say, here's our reactant. We go over some point to here. This is the intermediate, and we go over another hill to get to our product. Now, we'll learn all about this diagram. You don't need to know it now. But this is just an example, okay, where you have this profile, but we're not talking about the structural changes. We're talking about the energy changes. So this is energy, and this is coordination, it's called. Not time, but coordination. So it's the changes in the molecule. That's what we mean by coordination. So through coordination changes, energy goes up and down. So here's the reactant, and if you look all the way over to the product, it's lower. And that's usually assumed because that's why we learn these reactions. They become more stable. So that's one thing to consider is where did you begin as a reactant? Where did you end as a product? Did you end higher or lower? We'll learn things like exothermic, endothermic, exergonic, and endergonic, but not now. This is just an introduction, okay? Also, how high of a hill do you climb? So this right here, the hill, is known as the rate of the reaction, the kinetics of the reaction. So going from R to P is what's known as thermodynamics of the reaction. Going from the step that you began to the highest hill that you have to climb, that's known as the kinetics of the reaction, the speed of the reaction. So these are things that we'll learn about, and that actually covers D. We could also talk about the orbital description of the reaction, right? And we'll not do that now, but we'll learn all about that as we go through the whole semester. So when we describe a reaction mechanism, we'll also describe the orbital changes that occur in that mechanism or during that mechanism. Okay, so that's what this is. Now, the idea of an electrophile or a nucleophile, this is something that you should definitely know right now, so I'm going to write it out. An electrophile is, remember, phile means loving, right? So something that's electron loving. Now, who wants electron? Who wants negative? Positive. So this is when something's positive, it wants negative. It wants electrons. A nucleophile is nucleus loving. Now, what's a nucleus? Nucleus is where the protons are, positive. So a nucleophile is something that has electrons, and it wants to find a positive source to counter that. And so those are things that want positive. So negative wants positive, positive wants negative. If you're negative, then you're a nucleophile. If you're positive, then you want negative. You're an electrophile. See that? So those are terms. So going back up to our reaction, since the alkene is having electrons, okay, what does it want? It wants a nucleus, the opposite of electrons. So this right here is a nucleophile, okay? And the H plus, for HCl, if you think of HCl, it wants to take electrons. So the hydrogen is an electrophile, right? Now, so the hydrogen is an electrophile. Another thing, look at the next step. Now the carbon's positive. What does it want? It wants electrons. So it's an electrophile. Cl is negative. What does it want? It wants positive, right? It wants a nucleus. So it's a nucleophile. I hope you see that. It's very simple. Acids versus bases, right? Base has electrons. It's a nucleophile. Acids have a positive, right? So they need electrons. They're electrophiles. So acids and bases. Bases are nucleophile. Acids are electrophiles. Okay. And then finally, how do we write equations? Well, I already have that listed up here. This is the way you would write it. you would draw this out the way I illustrate here. Now, one thing I want to point out over here, and I think there's another point where I mentioned this, but let's say I have A and it's going to react with B to become C. Okay? Now, this is no different than writing A reacts with B to become C. Notice what I did? I took B and put it over the arrow. It doesn't matter. It's the same exact thing. These are equal. Or I could write B reacts with A to become C. See that? I could write A reacts with B down below here to become C. There's no difference. These all mean the exact same thing. Why do you do this then? Well, sometimes the molecules are big, so you put some over the arrow to save space. Other times you put whatever is most important to you, your focus, what we call the substrate, the thing that we care most about, we put that before the arrow, and whatever is not as important, we put over the arrow. And so there's many reasons to do it. You can put it under the arrow. It's all the same stuff. Don't get confused about where these two things are. So this could be an alkene, an HBr. It could be an alcohol. It could be an acid-base reaction. It doesn't matter. The key here is that these all mean the same thing. So I happen to write over the arrow HCl. But if I put HCl below the arrow, same thing. Next to the arrow, right next to alkene, same thing. All the same. Okay? So that covers reaction mechanisms. Let's go on. Now let's talk about synthesis and retrosynthesis. Now, synthesis is the process of describing many reactions combined together. So remember, a reaction is where reactants become products. But what if you have many different reactions? Well, if you string them together, that's known as a synthesis. Now, it's very common that with synthesis, you're not going to show every step because you might have 5 or 6 reactions, and each reaction can have many steps. See, look, these are steps for a reaction mechanism, right? And if I had to write 6 of these out, and each one had 3 steps, that's way too much drawing on paper. So usually when we do a synthesis, we're not showing, or retrosynthesis, we're not showing the details of every single thing that happens. We're showing what we begin and where we end, what we begin, where we end, and we string reactions together. Okay? So multiple reactions combined is what makes up what's known as a synthesis or a retrosynthesis. All right, now here's an example of that. Imagine, without looking at that, our goal is to get to D. We want to make molecule D, whatever it is. Okay? Now, we start with A, we can go to B, and then B to C, C to D, right? Notice that I'm going from here, A to B to C to D. Now, going from A to B might be 5 steps. If you go into the mechanism of that, it might be really detailed. Bonds breaking, bonds making a few different times. But we don't care. We're going to show the big picture. So all we care is that A becomes B, becomes C, becomes D. Now, another thing I want to point out, notice how I'm describing this to you. I'm telling you A goes and becomes B, C, then D. When you go from the reactant, this is the left side, the reactant, towards the product side on the right, this is called a syn description, synthesis. So we're describing a synthesis from reactant towards product. But there's other ways to do this. What if I have D and I want to figure out how to make D? One way is to go from A to D. But what if it's easier for some reason, we'll learn why in a moment, to go backwards? What if from D we go back a step to C and back to B and then back to A? Well, that's called reverse. That's a reverse synthesis. We're describing in the opposite direction. We're going in retro, we're going from product to reactant. That's what it means to be a retrosynthesis. We're looking at our goal, our product, and we're working back until we get to the reactant. So from D back to A. That's the only difference between a synthesis and a retrosynthesis, is whether you're describing in the forward from reactant to product or product backwards to reactant. That's it. Okay? Now here's another example, and this is a real world example. And so our goal is to have an alcohol form. Now, there are many ways to solve or achieve this goal. And usually what people do is they see what they have in their lab, what they have available to them, right? So imagine if all I have is an alkene in my lab. So I'm running out of supplies. I only have alkenes, okay? And my goal is to make this product. Well, there are two ways I could show you how to do this. Like I said, one is forward. I could say, well, you take the alkene, you add H plus H2O. Don't worry about memorizing any of this, okay? We'll learn about that in a moment. But you put H plus H2O, now you have an alcohol. And from the alcohol, we use something called PCC, which is called pyridinium chlorochromate. Don't worry about the name, PCC. We'll learn about this one next semester, but for now we need to know generally. So PCC makes an OH become double bond O. This is a carbonyl. And then from the carbonyl, we bring in another carbon alkyl group, and they come together and we make our final alcohol. So I just described to you in a synthetic point of view, a synthetic forward reactant to product. Now, I could have done it the other way around. I could have said, all right, here's my product. What's a step back from that? That's retro. So I said, okay, from this product, let's go and put that. So we're going to go back a step, and we're going to have this carbonyl. And then from there, we're going to have an alcohol. And then from there, we're going to go back to the alkene. Notice that the arrow is still in the same direction. Now, that's because we're still going from reactant to product, but we're building the story in the opposite direction, backwards. We're looking at where we're trying to get to, and we're working back until we go to our starting point. Okay? That's retrosynthesis. Now, these are the points. The first one is, what reactions do we need to know for our exam? And that's the next page. We'll go over that in a moment. The next point, does it matter if I write over the arrow, under the arrow, next to the arrow? And as I showed you a moment ago, the answer is no. See, look, this alkene could be next to H plus or next to water. Maybe H plus is over the arrow. Maybe H plus is below the arrow. It doesn't matter. The only reason why I did it this way when I typed this out is because I didn't have enough space to make one line. So I tried at first putting the alkene next to water and H plus over the arrow. It wasn't enough space at. So I started throwing things on top of the arrow. And that's all we do. Another thing is, what is this about numbers, right? Look at this right here. I said, what about these numbers? Well, look at the last step going to the product. Notice how it says 1, then 2. That means that this is actually two different steps to go through this transformation. Remember, we're not showing the mechanism. So, but these are required during the mechanism. So to get this right here, this carbonyl, to become the product, first we need the thing that we have above, which is an alkyl lithium. It goes into it. And then 2, we need an acid. Without the acid, we're not done. So these are two separate steps. You could write 100 if you want. Okay? Obviously, you're never going to, but you can make many steps. Because if all that you care about is how this carbonyl becomes this alcohol, and it takes 4 steps to do it, you might write 1, 2, 3, 4, and then fill it all out. In theory, I could have written this whole reaction. I could have said we have an alkene becoming an alcohol, and then over one arrow, write 1 H plus H2O, 2 PCC, 3 the alkyl lithium, and then 4 H plus, and I am correct. This is exactly what we're doing. Notice how I combined everything by just writing numbers here? Now, on your exam, you don't want to do this because see, when you look at it from this point of view, you have to do a lot of things in your mind. And if the TA doesn't catch what you did in their mind, they're not going to spend time writing this out. So you'll lose points. So it is not recommended to do it this way. Sometimes on an exam, they'll give it to you this way, and they'll say, what's the answer? So they'll say, here's where you begin, here's where you end, here's what you're doing, what is the answer, right? Or maybe they won't show you the end, right? You'll have to figure that out. Okay, but I am telling you that you would never couple 1 through 4 over one arrow, not on a test, because then you got to hope they could, in their mind, see everything you're doing and not, do it too quick and then cross it as wrong. So not common for you to do this, very common for you to see this. Okay, so instead of writing everything out, you could see it like that. And here's a common question. Like I said, you might have this, and it says, what's the answer? Very, very possible on your test, multiple choice, or maybe even essay. So you have to kind of work through it. And you just unravel this into its steps that you see above. Okay. Okay, so that covers an introduction to synthesis and also an introduction to retrosynthesis. All right, and that's what we did here just now. Okay, now let's get into reactions. Okay, reactions are very important. In this case, we have 6 that we have to remember. Now, we don't need to know the mechanisms. We just need to know the overall process of what happens. Now, this is the beginning of retrosynthesis, okay? We're going to first start by doing synthesis, and we're going to build our way back to retro. Okay, now here's the story. What you want to look at is, number 1, the carbon that's changing in the reaction. So in this case, a carbon with a Br, right? This is an alkyl halide, and it's becoming an alkene. That's what this reaction is doing. Now, you have to realize that all reactions are changing functional groups. And remember back in the chapter 1 video, I talked about, well, actually chapter 2, I talked about the functional part of the molecule. So this molecule could be big, it could be 100 carbons, but the carbon that holds the Br and its neighbor is the only ones that are going to do this reaction. So the carbon and its neighbor are the ones that become an alkene from this reaction. And what do you need to do that? You need some sort of base, R3CO-. That's it. Okay? So these are the ingredients to make an alkene. If you have an alkene, you could make it into an alkane by using H2. Now, we don't know how it happens. This isn't describing the mechanism, but we do know that an alkene with H2 becomes alkane. H's come into it. That's it. That's what we see here. Okay? This is an addition reaction. H's are adding on to the alkene. Okay, that's all we know here. And notice again that no matter how many carbons are after on the left and right side of this alkene, it would just be the same at the end. It's just these 2 carbons that make up the double bond that become an alkane. That's it. All right. Now this carbon has an OH. And when you use PCC, which is known as pyridinium chlorochromate, not important for you, PCC makes an alcohol, or the carbon that holds an OH, into a double bond O. That's what's happening here. So that yellow carbon, again, I could have 1,000 carbons, but only the carbon with the OH will do this. The rest of it stays the same. Okay? That's what we're seeing. Now here I have a carbon, and by the way, so this is an alcohol becoming a carbonyl. It could be a ketone or an aldehyde, depends upon what's around it, but that doesn't matter. It's a carbonyl generically. Okay. Now, the next one is an alcohol becoming an alkyl halide. And how do you do that? You add HBr. And what happens? The carbon in yellow loses its OH and gets a Br. This is a substitution, right? You're swapping out the OH for the Br. Okay, now again, we don't know the mechanism. We don't care. All we know is that's what happens. All right, the carbon with this Br here, for this next one, so carbon with Br becomes carbon with lithium by adding lithium over the arrow. So alkyl halide becomes what's known as an alkyl lithium through this reaction. Now this by itself is usually followed up with the last reaction that we have to know, and that is an alkyl lithium. So alkyl lithium, again, the carbon with lithium, we're going to replace the lithium with the C double bond O carbon. Now watch. Let's say this is red. It's very important that you color code. This is red and this is blue. So the red and the blue are going to connect together. Whatever the red carbon has, it still has at the end besides lithium. And the blue carbon, so here's the blue carbon down here, and here's the red carbon. The blue carbon has an OH, and then whatever else is connected to it. So the blue carbon, in this case, only has H's on it, so it has H's again. But if there was carbons, you bring it all in. And so now I've made the connection between the red and the blue. That's the last recipe. So these are the ones that we need to know, these 6. You don't have to memorize them. They'll be on the front cover of your exam. And I'm going to show you a better way to organize this soon. But for now, you don't have to memorize. Just know how to use the recipes. So let's go through an example together. So here I have a carbon with a Br, and I have an alkene. So there, I can look over the arrow to figure out what I'm doing. In this case, I'm adding lithium. So when I look at my reactions, here's lithium over here on the right. So that's the reaction that plays a role here. And what it tells me is the carbon with Br, the Br gets erased and the lithium comes in its place. So let's do that. So the carbon, let's say in red, that has a Br is now going to have the same thing. Notice I draw everything out exactly as I see it, but this red carbon now has a lithium. That's the difference. Okay, that's it. Now, the red carbon with lithium, I'm over the arrow, and by the way, remember, it could be next to the arrow, over the arrow. It doesn't matter how you organize this. It all means the same thing. But over the arrow, I have this carbonyl, this blue carbon. So remember, the carbon with lithium and the blue carbon connect together, but I carry everything else with it. So here's the red carbon drawn out again with the alkene and all. And now it is connected to a blue carbon right here. So here's my blue carbon right there. Now, look at my little diagram. It says to me that the blue carbon has an OH on it, so the double bond O becomes OH. Let's fill that in. Now, could you draw the OH up, down, left, right? They all mean the same thing. So you could do it either way. So let's say I draw the OH like that. Now, I also can't forget about the other pieces. So the blue carbon, notice over the arrow, it has a yellow right here, methyl. So I got to put that back in. So here's a methyl. Again, draw it down, draw it up, draw it left, draw it right. They all mean the same thing. So the key is I connect the red and the blue together, and I carry everything else with it together. Okay? And there you have it. Now, the next reaction says PCC. So if I look over here on the left bottom, PCC makes a double bond O from a carbon with OH. So I'm going to trace everything out as I see it, and I'm just going to put in the blue carbon right here. Instead of an OH, it at the end has a double bond O. That's what the instruction tells me. So double bond O. And that's it right there. So I've done that step. The final step is where we take H2. Let me move this down. So H2 and palladium. So now I'm going to take H2. Now, if I look at my instructions, it says to me over here, right here in blue, H2 reacts with alkene, double bond carbons. It does not react. Nothing in this chart tells me that it reacts with double bond O. So if I trace everything out the way I see it, here's the double bond O. I'm going to leave double bond O alone because that's not an alkene. But the alkene is gone. So all I'm doing is making this double bond disappear. That's it. You don't have to show H's there because it's a line drawing. So you could leave out the H's, but the H's are there. So H2 adds to the double bonds. It's an addition reaction, right? So that's all we're doing. That's it. So notice how easy. This is our reactant over here. And I went from reactant to product by following the recipe here and using my chart as a guideline. But what's most important is that you realize everything gets carried along with it. Please don't just break pieces apart. And realize this is just a little chart, a chart that can be any molecule. We're looking at the functional location within any molecule. If a molecule is 100 carbons and it has a Br on one of them, that's the carbon that's going to do something. And that's all we're doing here. So I want you to try these next two. Try B and C. Pause the video. Give yourself a chance to do this. And then I'm going to go over it with you right now. Okay? Following this video is a whole bunch of other problems that you're going to do. But right now, just take a moment and see if you could solve these. Okay? So I'm assuming that you did that. And now let's get started. So the first thing is I see a carbon with an OH and PCC. So I go to my chart and it says to me, I'm going to do it. You could see it for yourself. I do recommend you print out these reactions so that you could see them by themselves, okay? So the carbon with the OH becomes double bond O. That's what PCC does. So I'm going to trace everything out and make it double bond O. Here's the red carbon. That's all. That's the only one that actually has a change. Now, the next one is where the carbonyl is connecting to the carbon with lithium. Notice how I switched it. I put lithium over the arrow instead of to the left. Over here in our diagram, lithium is on the left, carbonyl is over the arrow. It doesn't matter. It's the same thing. The key is that the carbon with lithium and the carbon that has double bond O connect together. So let's do that. So let's say this is blue. I'm changing the colors around. It doesn't matter. It's our reference. So what I'm going to do is I'm going to have, let's say this right here is the red carbon right here. And it's connected to the blue carbon. Let's say right here. This is the blue carbon. Okay, so notice how I traced out all the red carbon. There's 4 carbons. And now I have 3 after the blue. 2 after the blue. Notice how there's 2 carbons. So 2 carbons. Now, what else do we do? Well, the red carbon has an OH. I'll draw it up. You could draw it down. You could draw it to the right. It doesn't matter. But the red carbon now has an OH instead of double bond O. That's the key here. You see that? So all I did is connect everything together. Now the next one says I use HBr. So I look at my reactions. HBr with an alcohol becomes alkyl bromide. So I trace everything out exactly as I see it. Here's the blue carbon. Here's the red carbon. And instead of an OH, I'm going to put a Br there. And that's the answer. You swap. This is called the substitution. We're substituting an OH for a Br. And that's what we did here. Okay? Now, the next one is lithium. So I look at my chart, I find lithium, and it says alkyl bromide, remove the Br, put a lithium in its place. Okay, so let's do that. Here it is. Here's the blue carbon. Here's the red carbon. And here's lithium. Right there. Done. Finally, we take the carbon with lithium and we're bringing into it a carbonyl, right? All that. Now, look, this is the blue carbon. Well, let me do green since I already have blue. Here's the green carbon. So I'm going to trace everything out on the right side. Here's the red. Here's the blue. And now the rule is take out the lithium and connect the red to the green in my color case, right? So here's the green carbon right here. Green carbon. Now what's on the green carbon? Well, it's always going to have an alcohol. That's what the instruction shows me. So I'm going to put an alcohol. Let's say I put it here on the right. It could be up, down, left, doesn't matter. What else does it have? It has 3 carbons. In the middle of the 3 connects in. So 3 carbons in the middle of the 3 connects in. And now I'm done. This is my product formed. See that? This is the reactant. So I started with this alcohol, went through all these different steps to get to this down here, an alcohol, but much bigger now. And that's what we did, going in the synthetic direction, in the forward direction. Okay, let's try C. So here's the carbon with an OH. Instruction tells me HBr, replace the OH with a Br. So let's do that. Put a Br right there. Okay, now lithium. Lithium replaces the Br. So let's replace it. Lithium, right there. Here's the red carbon. And then finally, over here it says carbonyl. So I know this carbonyl in blue, everything's going to be carried along with it, but the blue carbon connects to the red carbon, right? So we're going to go ahead and do that. So we go like that. Here's my red carbon. And now it is connected to the blue carbon. Let's go here for blue. What does the blue carbon have? The blue carbon definitely has an OH. It always does, right? That's what it tells us in our instruction. And then don't forget that carbon has 3 methyls. It's called the tert-butyl group. We'll learn about that during the next chapter. But for now, that 1 carbon here has 3 carbons touching it. And now I'm done. This represents that yellow group. See that? So everything's connected together. So here are 3 examples of how to do synthesis, how to do a forward synthesis where you take your reactant and go through a bunch of steps to get to a product. And this is it. Okay, now again, not steps, but these are actual different reactions. Remember, each one of these reactions could be 3 steps, 4 steps, 5 steps. We're not looking at each step of the reaction. We're not looking at the mechanism. We're looking at the overall picture. Okay, so this is an example of synthesis. Now, let's go on with retrosynthesis. Now, retrosynthesis, remember, is working backwards. If we have a product, how do we go back to the reactant that we're trying to get to? So that's what we're going to do. Now, you could think of retro, just like synthesis, in 2 separate goals. The first goal is converting your functional groups from one thing to another. So functional group conversion. So here's an example. If I have an alcohol as a product, notice that this is my product, then a step back from this, if I go back a step, then it's a ketone. See that? So that's 1 step going backwards. From there, alcohol. That's another step back, and alkene is the final. Now, how do I know to do this? Like, what would be the basis of doing this? Well, I'll tell you right now. We have a very simple goal. Whatever they give you as a product, your goal is to get back to the alcohol. That's it. You always want to get back to an alcohol, and you'll see why in a moment. But that is your goal. So let me write down our goal. Our goal is to go back to alcohol. Now you say, well, what if I'm already an alcohol? Then you're done with your goal. So if they give you a product and it is an alcohol, you're done at that moment. But if it's not an alcohol, you got to figure out how to get back to an alcohol. And you'll see examples in a moment. But here's an example of, functional group conversions. And now let's take a look at an example of carbon-carbon connection. That's your second goal for retrosynthesis. See, here's the story. They're going to give you something big. And they're going to say, show me how to make this. It's a product, right? How to make this product from 4 carbons or less. So you got to go and take this product and figure out when can I actually separate the 2 carbons of the molecule from each other. So look at our reaction diagram. There's only one reaction. Let me erase this, actually, it'd be easier. So this is the only reaction right here that I just cleaned up that allows us. So if we have an alcohol, notice how this is an alcohol. If we have an alcohol, then the step back, remember we're going backwards, the step back from that alcohol is where they were 2 separate pieces. So that's when 2 different carbon groups can come together. So that's why, and this is the only one so far that can allow carbons to make connections. So your goal is always to go back to the alcohol, because once you get back to the alcohol, you're ready to break it apart into 2 different things. You see that? Let me show you. So let's say this is our goal. Now I'm going to show you something even before. So let's say that this is a let's say it's a double bond O. Okay, something simple. Now you're going to say to yourself, okay, this is a goal. This is the product, right? And how do I go back to the beginning 4 carbons or less? So you're going to say, well, my first goal in working backwards, is to go back to an alcohol. So you ask yourself, is there a reaction that allows for an alcohol, like let's say the step back, this red carbon, could that have been an alcohol and it became double bond O? If you look at your diagram, you'll see that, yeah, if I use PCC, then the red carbon could have been 1 step back. Remember, we're going backwards. This could have been an alcohol. And so now I'm back to the alcohol. That's always your goal. Get back to an alcohol if they don't already have you as an alcohol. So now that I got back to an alcohol, sometimes it takes more than 1 step to get back to an alcohol, and sometimes it's right away. Okay, so you'll see examples of that in a moment. What do you do next? That's the next question. So now that we're back, this is where we're able to actually break this apart. Notice that right now, this right here is 1, 2, 3, 4, 5 carbons. It's 5 carbons. If we want 4 carbons or less, we need to break it apart. Here's the rule. And I'll show you how the rule works by giving you first an analysis of the chart. Okay, so here's our chart again. I'm going to clean it up once again. And I want you to recognize something. That notice how the blue carbon and the red carbon are the ones that connect together. Here's red and here's blue. So really, between that carbon that holds the alcohol and one of its neighbors, in this case the red carbon neighbor, that's where you separate from. So it's always the same thing. The carbon that holds the OH is going to break from one of its neighbors. Now sometimes there's more than one neighbor. And let's take a look at an example of that soon. But for now, whoops, let's finish this one up. So here's the carbon right there that has the OH. How many neighbors does it have? Well, it has a blue carbon neighbor and it has a green carbon neighbor. There are 2 neighbors. Now, I could break this on the left or right side. I'm allowed to do that. So you might say, well, how do I know which one to do? Well, in reality, they both can happen. Let's see the difference between them. So if we look at our instruction, I'm going to draw two different arrows back. I'm either going to break on the green side. So if I trace it out, it looks like this. I'm going to trace exactly what I see. Here's the green carbon, and then here's the red carbon, okay? And then here's the O that was attached. So now what do we do once we break them apart? Well, here's the rule. The carbon that's OH initially was double bond O. So just make it a double bond O, and you're done with that side. So here's the side, the red, and here's the blue. Now, what about the green carbon? The green carbon was the one with the lithium. So all we do is we put a lithium on that green carbon, and now we're back a step. And that's it. What do you write? Well, then you write step 2, H plus. That's part of our instruction that you see in our diagram. So you just have to have number 2, H plus. Now, these two pieces can come together to give us that top molecule. But I could have broken from the red and blue side, right? So I could have gone like this. So I could have it where this is the green carbon. Here's the red carbon. Now, the rule is the red carbon, the one with the O, was double bond O. And then the blue carbon, the one that has nothing but just like that carbon, you have to put a lithium on it. So let's put a lithium on it, lithium. Now, these are both answers. Step 2 is H plus. Notice I wrote step 2 on top of the arrow. It could be below, on top, doesn't matter. Now, these are two possible examples. Do you see that the left one makes more sense for us? Because we want to go back to 4 carbons or less. And notice that right here, this has 4 carbons. This has 2 carbons. So they're both good. We don't have to go back any further. But in this case, I have 5 carbons and 1 carbon. We don't want that, because then we have to keep going back with the 5 carbon and make it 4 carbons or less. So even though they both can happen, we would pick this one as our winner, because we're done. We're now at a place where it's 4 carbons or less. Okay, that's all we're going to do. Now let me again summarize what I just described. You want to get back to the alcohol from whatever they give you, because once you do that, you can take the carbon with the OH and break one of its neighbors and separate. And what makes you decide how to separate is going to be based upon how you can do it so you get 4 carbons or less on both sides. That's all you're going to do. Okay, so that's the basic logic here. Now, one other thing I want to point out. Notice that I put this right here, this carbonyl group, I put it next to the lithium carbon. I could put it over the arrow. It's fine. You could take it and draw it over the arrow. Why would I put it next to it? Well, usually the only time that you put something next to it is if they both need to be built even further. If you have to keep going back, I could split an arrow from this one and that one and keep showing how to go back to 4 carbons or less. So that's when you definitely don't put anything over the arrow. But if something is good as is, you don't have to modify it for the carbon. You could just throw it right over on top of the arrow. So I just chose not to do that here. But I want you to realize the only time that you wouldn't put something over the arrow is if it's not 4 carbons or less, if it's more. Otherwise, you could. So I could have taken this right here and put it right up over here, well, like that. And that's fine. That's perfect. I could write number 1, that, and then number 2, that. And that's fine. Okay, so I want you to see that. So don't worry about how you draw it out, and don't worry about how you see it drawn out, because it's all meaning the same thing. Okay, so that is right here the way this works. Again, very simple, right? I hope you're getting the point. You're gonna, I promise you, by the time we're done, okay, you're gonna, this is easy once you're actually have a little practice with this. All right, so what is our priority? Just to summarize these notes here. So we always go functional group conversion until we get back to an alcohol, and then once we get to the alcohol, we start breaking up the alcohol into 2 pieces. And if we have to, we do it again. We just keep going back to another alcohol, break it up into 2 pieces until you're finally done. That's all we're doing, is going in retrosynthesis. Remember, this is retrosynthesis. So you're going to go from your functional group conversion back to alcohol, and then separate the carbons. That's it. And so that's all that everything here is describing. So I'm not going to read this. You guys can read this for yourself. But everything here is just description of what I just said. And as I mentioned here, it's freaking easy. It is freaking easy. Trust me, you're going to love this. You're going to hope that you have 50 points on your exam with this. It's freaking easy once you get it, okay? So, but you have to practice to get to mastery. All right, and we're going to do that. All right, now, before we begin, there's two other things I want to mention. The next page, I'm not going to read it to you, but some people like to read something when they start learning a new topic. This really is a practice type thing. But I wrote something out for those who like to think in a logical way on paper. I shouldn't say logical. I mean, this is all logical, but something that gives you like a recipe. Okay, that's the first thing we're going to see. But as I mentioned here, I promise you, you're never going to need to write this on your card. It's going to be intuitive for you. It's just something to get started with. The second thing I'm going to show you is actually, in my opinion, very useful. I took the 6 reactions and I organized them in a way that's more intuitive for you to work with them. And I'm going to show that one to you. And that I think you should put on your card. I came up with this a few years back and people love it because it's so much easier than looking at the 6 reactions the way that you see it now. So let's go through the first one. So again, I'm not going to read this to you, but basically what I'm writing here is that your goal is always to get back to an alcohol. And so the first thing you're going to do is you're going to look at what they're giving you. If they give you an alcohol, then this is the instructions on how to get back to 4 carbons or less. You're going to break and split, and everything that I'm going to show you in practice is written here for you. But when you're done, you ask yourself, are you done? You work back, you say, am I done? Well, if one side is more than 4 carbons, then you're not done. So you just repeat the process again. That's all you do. And these are the different functional groups. So if they give you a carbonyl, this is the recipe of what to do. If they give you an alkyl halide as a product, then you go back, this is the recipe. And that's it, alkane and alkene. These are the functional groups that they can give you as a product, and you work back until you get to alcohol. That's it, okay. So again, read this, but again, don't worry about how big it is because you're not going to need it. This is the chart that, in my opinion, is going to help you the most. Here's how this works. This is organized in a way to get us back to an alcohol. I want you to think of it like this. Let's say you have to go different directions to get to a certain destination in your car. But there's that one point where everybody has to get to. Let's say it's the Bell Parkway. So you might go to the Southern State and get back to the Bell Parkway. Someone might be coming from the LIE, get back to the Bell Parkway. Someone might be coming from the Northern State, find their way back to the Bell Parkway. They all go back to the Bell Parkway, and then from there you get to wherever you got to go from there, right? Okay, that's the idea. Wherever you begin, you want to get back to an alcohol. Everybody gets back to the alcohol. That's your goal. And if you're already an alcohol, if you're already on the Bell Parkway, you don't need to get to the Bell Parkway, right? Well, if you're already an alcohol, you don't need to go back to an alcohol. You go from there and break apart. Okay, so this is the trend. If you have an alkane product, then you have to go through all these steps to get back to the alcohol. Alkene, alkyl halide, and then finally alcohol. So you're going to use this as a guide. Now remember that this is just 2 carbons, but it could be 1,000 carbons. If it's an alkane, it's an alkane. You would just figure out, okay, going back a step, I need to put a double bond somewhere. So you figure out where's the best place to put it. I'll show you how to do that soon. Then you go back and say, okay, now I need to put a BR in. Notice that the carbon that's double bond is the carbon that has the BR. Okay, go back a step. You need to put an alcohol on the carbon that had the BR. You're going backwards, and now you're at the alcohol. Once you're at the alcohol, you break to 2 separate sides, and that's what I'm showing you down here. One becomes RLI, and the one that was blue is double bond O. And if you have to go further back from the RLI, let's say it's very big, then you go back to an alkyl bromide. So you go back to here. The R is now with the BR, and then you drop this up to the top of this little diagram right over here, and you do it all over again. So once you break things apart, if the alkyl lithium is no good, then put a BR and go back up to alkyl halide, work down again. So you keep going up, down, until you're finally done. If you have a carbonyl, then the double bond O carbon, the blue carbon, if you go back a step, was an alcohol. And you have PCC in order to do this. So you go back. So let's say, for example, this side, when you separate 2 carbons from each other, if the carbonyl side is too big and you got to keep going back, then start here and go back to the alcohol and break again. That's it. That's what you're going to do. So I think that this is the most useful chart because it gives you a logical progression about how to go through this working backwards. Remember, this is the Belt Parkway. And these are just different paths to get to the Belt Parkway. And so if you're an alkane, you got to go back to an alkene, then back to an alcohol, then back to an alcohol. If you're a carbonyl, you go back to an alcohol. If you're an alcohalide, you go back to an alcohol, right? You see, if you're an alkene, alcohalide, alcohol. And that's it. And then once you do that, you break. All right, now it's time. This is it. This is where the fun begins because now you're going to actually put everything together and you're going to love this. Now, again, not everybody likes this, but everybody agrees it's fun. It really is fun once you get the hang because you're kind of like working with reactions and it's kind of cool. It's not really too hard, but when you see it in class, oof, you're like, wait, what the heck is going on? How did he do? What did he do? Now I think it's clear, right? All right, so let's go for some practice together. The first thing is I have an alkyl halide, and I want to go back to what? The alcohol. So I look at my chart, and the carbon that has alkyl halide, one step back, and it says over the arrow is HBr, and I have an alcohol. So let's do that. Let's draw this out. One step back, put HBr over the arrow, and the carbon in green is now an alcohol, OH. And I'm back a step, right? Okay. Now what do I do? Well, now the rule is the carbon in green that has the OH, one of its neighbors you're going to break. So it's either the red carbon or the blue carbon. Those are the only two neighbors to that green carbon. Now it makes no sense to break by the blue because then when you separate it, the green side is going to have a whole bunch of carbons, more than 4. So let's break right there, right? If we break between the red and the green, now we have 4 or less carbons on both sides. So that's what we're going to do. We go back a step and we trace out, let's say here's the red carbon, right? And now I could put it over the arrow, I could put next to the arrow, I'll put it over the arrow. So here's my green carbon, and there's the blue carbon that kept together with it, right? Now, what's the rule? Well, the carbon that has OH, if you look at the chart over here, the carbon in blue that has OH is now double bond O. And the carbon that does not have the OH has a lithium. Okay, so this green carbon is a double bond O. And that's it. And this is a lithium. And then you write step 2, H+. That's part of the ingredients that we learned about. That's it. 1 is the carbonyl and 2 is H+. We're done. This is 4 carbons or less, right? So we're done. Everybody's happy. And we answered this problem. Let's do another one. So I'm starting with the carbonyl, right? Carbonyl. So I look at my little road map and it tells me PCC and draw an alcohol wherever the carbon with the O, double bond O is OH. So going back a step, right? We're going back. This is my product, and I'm trying to go back to a reactant that's 4 carbons or less. So if I trace this out, here's the carbon, let's say in red, right there. There it is. Well, that carbon is an OH, and PCC is put over the arrow. Now I'm back closer to the reactant. And did I get to my goal? Yep, I got to the alcohol. So I'm ready to break. And so in this case, I only have one neighbor. The red carbon only has one neighbor. It has the blue carbon. So I could only break between the red and the blue. When I go back a step, I've got this right here, and I'll put this over the arrow since it's one carbon, the red carbon. So here's the red carbon. It's only one carbon. It's small. I could throw it right over the arrow. That becomes double bond O, just as I see it. Step 2 is H+. This is step 1. Now notice the red carbon doesn't have the blue anymore, but it has H's. So you could put the H's in. That's pretty common for this when it's aldehyde, formaldehyde. So that's that. Now here's the blue carbon right there. So what do? I put a lithium on it, right? So I'm going to put a lithium right there. Now, I look at this and I say, wait, I'm not done. This is 1, 2, 3, 4, 5 carbons, not done, right? So I got to keep going back. So what is my goal? Well, the chart tells us that if you're not done after you get an alkyl lithium, you got to go back a step to the alkyl halide and then drop this up to the top of the alkyl halide path and go back again. So I'm going to do that now. And I think it's getting clear, so I'm going to stop going to that chart. But the carbon that's in blue, go back a step to Br. So now the carbon in blue has a Br. And now I take this alkyl halide. This is an alkyl halide, right? And so I look at my roadmap and it says go back to alcohol, right? So from here, OH. The blue carbon has an OH. What do I put over the arrow? HBr. What do I put over this arrow? Lithium, by the way. I almost skipped that. Always put stuff over the arrow. Just look at your chart. Now, I'm back to the alcohol. I'm good. I'm ready to break. And once again, this blue carbon only has one neighbor, green. So I could only break there, right? So if I go back a step, then I could trace out, here's my green carbon, and then let's say here's my blue carbon. Well, the blue carbon holds the O, so it's double bond O. And the green carbon is the one with nothing on it, so it has a lithium. And this is step 1, right, with H's twice on it, because there's nothing on that blue carbon but an O. And then step 2 is H+. And now we're done. We're back to 4 carbons or less for everybody. That is it. This is how it works. I hope you're getting it, okay? So that's basically A, and that's B. Let's do another one. Let's do C. Every one of these is a different functional group, so I can teach you the rules, and then you'll practice on your own. And then I'll do the video solution. All right, where's the functional? Right here, carbonyl. So we have a carbonyl. I look at my little road map, and it says carbonyl, 1 step back to alcohol, right? So from here, trace everything out that you see and make it an alcohol. So here, the green carbon is now an alcohol, right? What do you put over the arrow? PCC. Remember, we're going backwards. We're working backwards to get to the reactant. Okay, from here, I'm going to break, because once you get to alcohol, you break between one or the other side. So I could break on the blue side, or I could break on the red side. Whatever carbons are touching the carbon with the alcohol. It makes sense to break on the blue side, right? Because well, no matter what, we have to keep going back, but let's at least kind of give a little bit of space on the other side of it. So I'd rather break over here, simply because at least one I can start as is, and the other I'll have to keep working back. So the one that I'm working back is this, right? The blue side. So I'm going to put that not over the arrow, but I'm going to put it before the arrow. But since the green side is good, I'm going to put it over the arrow, right? Like, whoops. I'm going to put that right over the arrow because I don't have to go back any further. So here's green, here's red, red. And the carbon that is green has a double bond O. That's step 1. And step 2 is H+. Now, the blue carbon, we have to put a lithium on it, right? So put a lithium. And now we're back. But again, this is more than 4 carbons, so we can't stop here. We have to keep working back. So let's go back another step. What do? It says if you're not done, then put a Br where the lithium is. Lithium, put a Br. So I'm going to work back from here. And what's the rule? The rule is the alkyl halide, you go back to an alcohol. So going back a step, it's an alcohol, and over the arrow is HBr, right? That's just my recipe that I'm reading. If this is the blue carbon, then it's the one that had the OH. Now I'm ready to break again. So let's say this is the only neighbor, red carbon. So let's break between blue and red. So if I go back a step from here, I could break between the blue and red. And so actually everything is good as is. This is the red carbon. And the blue carbon I could put over the arrow, or I could put it next to it. It doesn't matter. Let me show it next to it this time. So like that. That's the blue carbon. And then in this case, I'm going to write step 2, H+. And now the red carbon, just put a lithium, and you're done. See that? They're both 4 carbons or less. I could have put the lithium on top of the arrow, the blue carbon on top of the arrow. It doesn't matter. You don't want to put both of them on top of it. You need something before the arrow, right? But you could do either one. It doesn't matter. All right, so hopefully that's clear. And that's just another example, getting back to 4 carbons or less. All right, let's see another. There's 2 more to go. Alkene, alkane, and then it's time for you to practice. So for this one here, what do? Well, look at our chart. It says to us if you have an alkane, that's the one that has the longest path back. Alkane's all the way up here. You got to go all the way back down to alcohol. The first thing you need to do is figure out where can I put a double bond. See, the first step back is alkene. So let me go ahead and show you how you would analyze that. So I have all these different carbons, but two should be a double bond to each other. And so my thinking is, now let me show you actually before we go further. Notice that the carbon that's double bond, eventually, let's say in blue, one of the two carbons that are double bond in blue gets a Br and then eventually an OH. So that means that you could think that one of the alkene carbons, if you think back, is going to be where you break from, one side of it. So knowing that, then what you should do is you should think, where can I put a double bond so that I know going back, eventually it's going to be an alcohol there, one of the carbons, and if I break, it'll be 4 carbons or less. See that? So watch. If I look at this, and let's say I put a double bond here. Now you could put a double bond anywhere you want, but I'm trying to put in the middle so that when I break, it's 2 separate pieces and hopefully 4 carbons or less. See that? So if I do this, eventually I could break between those 2 double bond carbons and it will be 4 carbons or less. So that's a good place. If I put it here, it wouldn't work as well because I would definitely have a big piece down below. So that's what I want you to think about when you're dealing with alkane. The first thing is, where should you put the double bond? All right, so let's go back a step and do that. So now I go back and I draw this out and I decide to put the alkene here. There's other places that you can do it. There's more than one answer for retrosynthesis, but that's where I'm going to do it. Okay, so what did I do? H2 over the arrow with palladium. Now let's go back from here. Now the next step back from an alkene is an alkyl halide. So one of these 2 carbons is going to have a Br. That was the step back. Now again, let's be strategic because the one that has the Br eventually gets the OH. So does it matter where I put? No, in this case it won't matter. I could put it on the left or right double bond. It's one of the 2 double bond carbons, but in this case it won't matter which one. So let's say I put it here. Again, you could have put it on the other side. Either one of these 2 carbons could have had the Br going back a step. Now sometimes it might be where it's better one place than the other, but not in this example. Okay? So over the arrow, what do you write? You write R3CO minus. And now you're back a step. Actually, that reminds me. Let me make sure, because I used to have OH minus. Yeah, I do. Good. So actually change this to R3CO minus, because that's what he's using this year and last year, but I forgot to change it last year as well. So it's R3CO minus. Hydroxide does the same thing, but it's a little bit, don't worry about why, but just change it to that. Okay, continuing. Now, what's the next step back? The next step is where the Br is an OH before. So let's do that. So let's trace it back. And now there's a OH right there. So let's say this red carbon, it had the Br. Now it has the OH over the arrow, HBr, right? That's what you're supposed to do when you look at your recipe. We're finally ready to break. Now, what we're going to do is we're going to break in a way that gives us 4 carbons or less. So I'm definitely going to break here, but I could break up here. I could break, I don't have another color, I'll do yellow over there. I could break in any of these 3 positions. The red carbon is all that matters. One of its sides is where I break. And you're thinking, which way can I break to get 4 carbons on both sides? And the answer is the blue and the red side, right? So let's see what that looks like. All right, so if I go back a step from here and I separate, I'm going to put the blue over here, okay? And I'm going to put the red side over there. So here's the red carbon, here's the green carbon, and here's the yellow carbon. Now, the rule is the carbon that has no O on it is put a lithium, and the carbon that has the O is double bond O. And these are my 2 starting materials. Over the arrow, I could write step 2 H+. Now, I could have put the lithium side over the arrow, or the the carbonyl side over the arrow. Doesn't matter, or next to each other before the arrow. All the same. I hope this is getting easier for you. Now, obviously, there's one more, and then you're going to do a practice on your own. So let's knock this last one out. And I hope by now you've been trying them on your own before I even get to it. You've been pausing the video. But if not, you're going to have plenty of practice coming up next. All right, so looking at our flow chart, we're at the alkene. What's the step back? Well, from an alkene back is alcohol halide. So let's draw it out. Now here's the goal. One of these 2 carbons is going to have the OH on it eventually. Which one should it be? And if you think about it, if I put it on the red carbon compared to the blue carbon, if I make the OH eventually on that red carbon, then when I break, it'll be 4 carbons or less. But if I put on the blue carbon I break, one side's going to be 5 carbons, right? So out of the two, it's not equal. I'd rather put it back so that the red carbon is the one that has the Br, because after that, you go back to it having an alcohol, and then I break, right? So there you have it. I'm picking the red carbon, and I'm doing it strategically so I don't have to keep building up the system afterwards. So that's the best place for it, right? So you'll see in a moment as I show you. Now, over the arrow, I write R3CO minus. Now, going back a step from here, the red carbon has the Br, so that's the carbon that has the OH, right? So here it is, red carbon. Here's the blue carbon. Now you'll get to my point. Now, by the way, over the arrow, we write HBr. Okay, now, the final step back. The red carbon could be, we could break between the red and the blue, which wouldn't be good, because that would give us the red side as 5 carbons, but we could also break between the red and the green. See that? Now, if I break this way, it's going to be 4 carbons or less on both sides. Actually, it'll be 4 carbons on both sides. So that's what I'm going to do. So you see how it all started here. If I put the Br there, then I'm stuck having to break eventually from that blue carbon to the neighbor, and that wouldn't ever work out. So this is the kind of forward thinking that you're going to do when you're looking through these problems. And as you can see, I'm pretty sure at this point you're saying, wow, I can see it. I'm not comfortable yet, but I'm getting there. Some of you probably are there now. But if you're not, I promise you just keep working at it with me. All right, anyway, so here's my two sides. Here's the red carbon, and let's just make it double bond O. That's the rule. The blue carbon's there. The green carbon, put a lithium on it, right there. Over the arrow, step 2H plus, and we are officially done. That's it. Let me make sure there's nothing else. So as you could see, guys, it's the same routine. Once you have your roadmap, you know to carry everything on, and you know to label. See how colors are important? I skipped that earlier part in the video where it asked about that. But the answer is yes. You should use colors if you can so that you can map things out logically. And I'm always going to do that when I teach with you guys on this, okay? So this is it for now. This is all you need to know about synthesis, retrosynthesis. It's your goal to start doing the problems. And I expect everybody to do their best. Try on your own. This is guaranteed to be 10 points on your test, maybe 15. Maybe it'll be a multiple choice and an essay. So definitely work at this. Okay, guys? So I'll see you soon.